Hi everyone. These are the video notes for your 5.2 guided notes. The title, Solve Radical Equations. And I am going to skip over the review and preview part at the very beginning just because we did that in at least, I think, 2 of my 3 classes, and you can use the video notes to fill those in if you need to. But what I'm going to do now is just jump right into my model problems. So the first one here, we're asked to solve for x here. And in each of these cases, our variable is in the exponent, and that can be really challenging because the way we sort of solve for a missing variable is we use a logarithm when that variable is in the exponent. And we have not learned logarithms yet this year. And that's essentially like the way we can take an inverse of an exponent, so get it out of the exponent place. But it's not the only way to do it if you have a common base. So, of course, after I said we're not going to do the review preview section, just to hop back here real quick. One sort of way to think about that is if you do have common bases and we have an equation, well, if the bases are common, so must the exponents be. And so we can write now just a linear equation saying, okay, if these guys match and they're equal to each other, then our exponents must also match. So if I were to solve this linear equation, I would just subtract 2x from each side and have 2 equals x, and that is my solution. And, we could plug it in, and if I plug it in, I'll have 2 to the, I'm going to replace it there, and replace the x here with a 2 as well. 2 to the 4 plus 2 is 6, is 2 to the 6. I don't even need to write that, expand that out to 64 to know that it's true. So you could actually stop right there and say, yep, that must be true. That's an identity. So let's take that same idea of, okay, if we're solving an equation and our bases are not the same, and we don't yet have logarithms as a tool to do that, what other options do we have? So we want to ask ourselves, is there a way to make the bases match? So for instance here, we're asking, is there a way to make this 8, to rewrite 8 using base 2? And the answer is yes, there is, because 8 is 2 to the 3rd power. So I can replace 2 to the x with, I can replace 1/8 with 1 over 2 to the 3rd power. And because that 2 to the 3rd power is in the denominator with a numerator of 1, I can take the reciprocal and rewrite that exponent as a negative exponent. So essentially what I've done is I've made my bases match. And now I can go ahead and force, I can write an equation that says that if my bases are common in an equation, so must my exponents be. So now I have my equation, x equals -3, and there's really nothing else to do with it from there. So we're going to leave that alone. Ta-da! So that was the first one. I'm going to call this A. I'm going to call this one B, even though it says E, and I'm going to call that one C. B is a bit trickier, right? And B is trickier because it's unsolvable. There is no way that we can represent a power with a base 3 as a 0. So this one actually has no solution because it is not possible to express 3 to any power as a 0. If you want to think about why that is, we could sort of take 3's and just write them to, different bases and see what happens, right? So 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 0, 3 to the -1, and think about what does that look like when we expand these out, right? So that's 3, 9, 27. As we make our exponents larger by 1, our expanded form goes up by a factor of 3. So I can sort of apply this logic backwards by dividing by 3 versus multiplying by 3. And so what's going to happen is no matter how small I make this exponent, I'm always going to have some value, right? So I can make this sort of infinitely large to the negative. This is still going to have value. It's never going to be a 0. So this one is, again, unsolvable. There's no real solution to that equation. For C, we have 9 to the x plus 1 equals radical 27. I'll slide this up. This one's a little tricky because 27 is a power of 3, not a power of 9. 9 is a power of 3. So we're actually going to kind of tackle both sides here. I'm going to rewrite this 9 as a 3 squared. And I'm going to rewrite that 27 as a 3 cubed. Okay. So now I have my matching bases, but I need to use my power or exponent rules to sort of clean these up. So when I do this left-hand side, I'm going to use my power of a power rule, which says to multiply. And here I want to recall that a square root is a root of 2. And I can rewrite this with a rational exponent as 3 cubed, but also root 2. So 3 to the 3 halves power. So we always have power over root when we're using rational exponents. So this is going to be 3 to the 3 halves power. And now that our bases match, we can set our exponents equal to each other and solve that way. So here I've got 3 halves. I'm going to subtract 2 here. I'm going to call it 4 halves just to make things a little bit easier for myself. I'm going to have 2x equals negative 1/2. Divide by 2, again, multiplying by 1/2 and dividing by 2. Oops, I think we ran out of space. Multiplying by 1/2 and dividing by 2 means the same thing. I don't want to have a complex fraction here, so I'm choosing to multiply by 1/2. So x equals negative 1/4 is our answer for this one, okay? So that was all just the very first problem. You can certainly write this out. It will not fit in your guided notes, but you can certainly write it out. I'll take some photos, you could print it out, and you can add that to your notes. What I want to make sure that you're doing is using this information to sort of apply to your own problem. So I'm going to pause the video. I'm going to fill in your problem, and then you can check the solution in just a moment. Here's the solution to your problems. Yours were a little bit cleaner, I think, than mine, so sort of like broken down a little bit more, so none of them had quite as many steps. So hopefully this was manageable for you. So I'm going to jump right back over into my problem number 2. Just going to get some fresh paper here. And again, we're going to solve these equations. So we no longer have our variable in the exponent. However, we still have to be sort of creative in how we combine common bases. And if we don't have common bases, how can we rewrite our numbers using common bases? So this first one here, so I'm just going to label these again, A, B, C, D, just so that we can sort of match the work here. And for my first one here, I want to sort of pay attention to the fact that this 3 halves power is only applied to the x. It is not applied to the 4. This is 4 times x to some power. This would only be applied to the 4 if this were in parentheses, which it is not. So the first thing I want to do here before I start trying to figure out how to rewrite base or 32 and 4 with the same base is actually divide out that 4 from each side so that I am dealing with just this power. And I'm sorry, I make my exponents really large so it's easy for you guys to see them. I want to make sure you don't think that's just a fraction. That's a fractional exponent, okay? So when we have a 3 halves power, again, that's power over root. So I want to think about this as the square root of x raised to the 3rd power. Now, you could place that 3 in the radicand instead. Order doesn't actually matter when we're doing powers and roots. What matters is like that you do something that makes sense for you. So in my case, I'm going to actually keep the 3 here because the first thing I want to do is take the cubed root of each side, and 8 is a perfect cube. So that's going to make a lot of sense to do in this case. So I'm going to take the cubed root of all of this, take the cubed root of all of that. And when I do that, the cubed root of 8 is 2. And the cubed root of this cube cancels, and I'm left with radical x. Now I don't want the square root of x, I want x. So I'm going to go ahead and square each side. Oh, I want my pretty green pen back. And squaring a square root, those cancel out. And now I have x equals 4. So that's my solution here. And if I plug it back in, okay, x to the 3/2 power 4 times 4 to the 3/2 power, does that equal 32? And it does, because the square root of 4 is 2, and 2 cubed is 8, and 8 times 4 is 32. So that's like a good check when we plug it back in. Okay, so that's the first one. The second one here, so part B, says, let's take x minus 1, raise it to the negative 1/4 power, subtract 2, and that gives us 0. So there's a lot going on here. Now we have a collection of terms being raised to the negative 1/4 power. I don't have to actually like try to expand this out to the negative 1/4 power, because my goal is to get x alone. So I'm actually going to like undo this. But before I can do that, I need to add 2 to each side. And when we do that, we'll have this x minus 1 to the negative 1/4 power equals 2, okay? Now, I want to cancel out that negative 1/4 power. And so I'm going to use my power of a power rule, which says that if I raise a power to a higher power, I can multiply my exponents. So my goal is to have an exponent that is invisible, right? No exponent, which is really an exponent of 1. So I want to think about what could I raise each side to, what power, so that that exponent of negative 1/4 becomes a 1. So the answer to that is the negative 4th power, okay? Because if I do this x minus 1, this power and this power will multiply to make a positive 1, which essentially means I don't need to worry about it. Okay, now 2 to the negative 4th power is 1 over 2 to the 4th power, which is 1/16. So that is now my equation. So a lot of stuff just happened, okay? If I add 1 to each side, if I want to sort of make this a little easier on myself, as I add it, I'm going to rewrite it as 16/16. That way I have a common denominator. It's amazing how much having common denominators matters again now that we're in pre-calculus. And when I add these two fractions together, I get 17/16. Okay, so that's the answer to part B. I'm going to just pause the video real quick so I can flip a page and start fresh for the other two questions on number 2. All right, I may not have given myself enough space for C here, but I'm going to do my best to clean this up, okay? And this one's it's a little bizarre because I have 2 to the x, and then I'm like multiplying by 1 over 32, which is the same as dividing by 32, but then it equals 32. So what I'm going to do is I'm actually going to multiply both sides by that 32 so that I clear that denominator right here. So these are going to go away. I'm going to have 2 to the x is the only thing that's left on the left side of the equation. I'm not really feeling like multiplying 32 by 32. And because I know I'm ultimately going to try to get a base of 2 anyway, I'm actually going to like rewrite this 32 as 2 to the 5th. And then I'm going to rewrite this 32 as 2 to the 5th as well. And when I multiply common bases with a, when I multiply powers with a common base, I add the exponent. So this is now 2 to the 5 plus 5, which is 10. And like all of a sudden things just got really cleaned up, right? So now if we have the bases match, the exponents match. So my answer, my solution is x equals 10. So that one started weird. You could have multiplied the 32s together, but then you would have had to like figure out what power of 2 that number was. So usually if you can catch that early on, it's going to save you a little bit of a headache. Here already I have this common base of 6, so I'm going to go ahead and add those exponents together. Remember, we're adding like terms, so we're combining the coefficients. Excuse me. And then over here, I'm going to recognize that 216 is 6 to the 3rd power, okay? And I know a lot of these powers because I just work with them all the time. If you don't know them, it might be a good idea to, and this is something we could do in class, or something I could add to Google Classroom, but just print out a list of like all the perfect, squares and cubes and, higher powers of the numbers from, let's say, like 1 to 10, just so that you start recognizing them, or you can easily locate them without having to bust out your calculator. So now that I have this, I want to think about, okay, if I move this up here so that I have my base of 6 that matches, this is going to be 6 to the negative 3 in the numerator, right? So I'm going to now just go, ooh, wait a minute. If my bases match and it's an equation, my exponents must match too. Therefore, x is 1. And that's the solution to part D, okay? So I'm actually only going to ask you guys to do the video notes for 1 and 2, because in helping some students sort of work ahead for problems number 3 and 4, it was really obvious to me that students would need a little bit more direction and instruction. And I think that that's going to be better to do in class together. So when I see you guys again, we'll save, 10, 15, 20 minutes of sort of direct instruction side-by-side modeling for problems 3 and 4, because at that point you would have committed, 20, 30 minutes already just to do the beginning of these problems, because they're pretty heavy. So again, I'm going to pause the video. I'm going to put the answers to your problem number 2 and then ask you to try them before you unpause the video, and then you can check your work.